Geometry, Unit 4, Lesson 4. I can simplify expressions with square roots. Okay, so if this is our example here, I want you to reduce or simplify square root of 48. There's a few different ways we can do this. I like to prime factor, so I'm going to zoom in for a second. And your goal here is to find perfect squares like 4, 9, 16, 25 that you actually know how to square root. But first, let's prime factor. What times what is 48? Well, you might think 6 times 8. But I can keep breaking these down. What times what is 6? 2 times 3. Okay, these are prime. I can't break them down anymore except for 1 times 2 and 1 times 3. What about 8? 8 breaks into 2 and 4. That's prime. 4 breaks into 2 and 2. These are all prime. This is called prime factorization. Now, here's the thing. If you look at any double numbers, those can be perfect squares. For example, we can see that 48 is equal to 2 times 2 times 2 times 2 times 3. So 2 times 2 times 2 times 2 times 3. But the thing is, I know 2 times 2 is 4. I know this is 4. And I know how to square root 4. In fact, though, 2 times 2 times 2 times 2 is 16. And I love this number because, again, it's a perfect square. I know how to square root that. So if I were to come over here, I could show you this. Square root of 48 is equal to square root of 16 times the square root of 3. 16 times 3 is 48. We got that from here. Why is this important? Because I know this square root, that's 4. I don't know the square root of 3. This is it. This is reduced, although you'll often see it written like this. Now, let's say you did this, but you didn't see that 16 was the factor you wanted to square root. So you would just end up having to do this a few different times. So take a look at this one. If you did 4 and 12, here's square root of 4 times square root of 12. You get 2 from the square root of 4. But square root of 12, you're not done. That's really square root of 4 times square root of 3. So you just keep going. Square root of 4, you know. It's going to be a 2. And then you know 2 times 2 is 4. So you have to keep breaking down the numbers underneath the square root symbol until there are no more perfect square factors. Perfect squares are the numbers you know how to square root. So if you don't see the biggest perfect square right away, it's okay. Just find one that you can see and then keep hunting for more. You can go ahead and try these two and hit pause. Okay, here I go to check your work. Square root of 54. I'm going to come over here and break this apart. It's even, so I know it's 2 times something, and if I go off to the side, I can see it's 2 times 27. Okay, that's prime. 27 is 3, times 9. 3 times 9. And 9 is 3 times 3. So square root of 54 is really 2 times 3 times 3 times 3. And that's important because I'm going to pick these doubles. 3 times 3 is 9, and I know how to square root 9. So that's going to be square root of 9. Okay, I used these two. And 2 times 3 is 6 times square root of 6. Double check. 9 times 6 is 54. I looked for doubles to find a perfect square. That's going to be 3, and I don't know square root of 6, so just leave it. Next one up, square root of 75. You can go do this right here. Okay, 75 I can already tell is 3 times 25. This is 5 times 5. So there's my perfect square, 25. 5 times 5 is 25. So I can rewrite this as square root of 25 times square root of 3. I know the square root of 25 is 5. And I'm reduced. All simplified. Next up, adding and subtracting radicals. You want to think about this just like we've done with like terms. Remember, like terms from algebra require us to only go with identical variable parts. So these are like terms because they have this exact same variable parts. The others are not with the x squareds, because this isn't x squared, it's x to the first. So this here is a like term with this term here, because they both have x to the firsts. So what I can do now is go ahead and combine them. 5x squareds and negative 3x squareds is just 2x squareds. Positive 4x to the first, positive 2x to the first is positive 6x to the first. I'm going to do the same thing over here. You can hit pause and try it yourself. Here I go. This is an x to the first. None of these are the same. X squared is different than x to the first, and y is definitely different. So this is it. It's done. That's your answer. Just like this was your answer. Okay, let's take this idea of like terms and let's apply it to radicals. They have to have not identical variable parts, but identical radical parts. So this is a square root, but it's a square root of 3. So you're good to go, plus another square root of 3. That's the key. This is like x squared, square root of 3, square root of 3. They have to be the same. So 2 square root of 3's plus 5 square root of 3's is 7 square root of 3's. You can try the next one. Okay, here I go. I don't see any the same, so oh well, I'm done. Careful. Let's see if we can first reduce. 5 square root of 8. This can be tricky. Square root of 8 is really square root of 4 times square root of 2. That's what this right here turned into. This right here is minus 3, but square root of 18, what times what is 18? Square root of 9 times square root of 2. I am really looking for these perfect squares because I know how to square root them. And this is really 1 square root of 3. There's a 1 in front. Let's reduce. This is 5 times what? Well, square root of 4 is really 2. Square root of 9 is really 3. And if we reduce, simplify some more, 5 times 2 is 10. Square root of 2's. 9 square root of 2's, and 1 square root of 3. Do we have any like terms? Here's a square root of 2. Here's a square root of 2. Oh, that's a square root of 3. Can't do anything with it. It's like x and y. 10 square root of 2's minus 9 square root of 2's is just 1 square root of 2 plus 1 square root of 3. However, you'll often see it written like this without the 1's, and that's your final answer. Okay, last page. And we need all of these for where we're going next. That's why we're doing it. Multiplying radicals, we're actually going to start with what we know, which is multiplying with variables. What you end up doing here is you can rearrange everything, and you end up doing 5 times 4 and x squared times x to the 1. It's really 5, this is 5 times x squared and 4 times x. It's all multiplication. So I can use the commutative property and do that. Most of you will skip that step and just go straight to here. X to the third. When you're multiplying the same bases, you add the exponents. You can try this one over here if you want by yourself. Okay, here I go. That's going to be negative 10. X squared, y to the 1. So let's take the same idea down here. You can rearrange them if you want. 2 times 3 times square root of 18 times square root of 8. This is 6, but here's my hint. You can do 18 times 8 right now and get a very big number. Or you can try and reduce them first. You know how to rewrite this and you know how to rewrite that. It's up to you. If you don't, and you just do 8 times 18, you get lucky, you get 144. It's a nice perfect square. But if it was a really big number, it would be harder to break down. You'd have to prime factor on the side. So you might consider rewriting this as 9 times 2, and this is 4 times 2. Might make it easier. It's up to you, though. So this is square root of 144, and square root of 144 is really 12. And 6 times 12 is going to be 72. You can try the next one on your own. Okay, here I go. I'm going to rearrange. That's 9. This is square root of 50. Square root of 50, though, I can break apart into square root of 25 times square root of 2. You have to try and reduce at the end. Square root of 25 is really 5. So I have 45 square root of 2. Okay, last thing. It's called rationalizing the denominator. We don't like to leave fractions or square roots in our denominators. We're not simplified if we do. So here's the first thing. How do you get rid of this fraction in the denominator? This 2 in the numerator is really 2 over 1. And this is 3 over 5. This is called a complex fraction because there's fractions in a fraction. And the way you undo it, multiply by the reciprocal here, multiply by the reciprocal here. This is really something over itself is really just the number 1. So you're not changing anything. But 3 times 5 is 15. 5 times 3 is 15. 2 times 5, I'm just multiplying straight across, is 10. 1 times 3 is 3. All of this turns into 1. And then you have 10 over 3. But what's 10 over 3 divided by 1? Well, just 10 over 3. Finally, you cannot leave a square root in the denominator, so the way you rationalize it is you multiply by whatever it is. Square root of 6 over square root of 6. That'll be the 1 that I multiply by. Square root of 6 times square root of 6 is square root of 36. 2 times square root of 6 is just 2 times square root of 6. If this was square root of 2, you could say square root of 12, but it's not. Now, we know square root of 36. That's why we just did this. Square root of 36 is 6. The numerator stays the same. But you're not quite done. You can reduce the 2 over 6 into 1 over 3. So you get 1 square root of 6 over 3. You probably won't see it written with the 1. You can try the last one on your own. Here I go. What are you going to multiply by to get rid of the square root in the denominator? Square root of 12 over square root of 12. That's 6 square root of 12 over square root of 144. 6 square root of 12 over 12. And yes, you can reduce here, not here. And that's going to be 1/2. So 1 square root of 12 over 2. But you probably won't see it with the 1. It'll just be square root of 12 over 2. Those are different radical operations, which you'll need for the triangles we're going to use in the next couple lessons. Good luck.